Okay, I think that's probably a good time to start. So, hi everyone, and thank you so much for joining us today for this seminar, which is part of the Causal Inference Interest Group seminar series that is supported by the UCL Center for Longitudinal Studies. And today I'm here with my co-host, Peter Tennant from the University of Leeds. Our speaker today is Marco Piccininni, who is a postdoctoral researcher in biostatistics at EPFL in Switzerland. His research experience spans description, prediction, and causal inference, and for several years he worked as an applied biostatistician in the domain of neuroepidemiology. And he's also worked on various topics related to causal inference methods. For example, he led one of the first applications of the front door formula in health, which led him to winning the 2024 Rothman Epidemiology Prize. So we're very, very lucky to have him present today. And today, Marco will talk to us about stability property of the risk ratio. So Marco, feel free to start. And for everyone else, feel free to put questions in the chat, but we will do the Q&A at the end of the talk.
Thank you, Georgia. Thank you for inviting me. Thank you, Georgia. Thank you, Peter. Yes, so I will present today a joint work with Matt Stensrud about stability property of the risk ratio, and I will talk a bit about what are the possible practical implications of this. So let's start maybe with a motivating example. So imagine you have a researcher who is interested in studying the effect of pre-exposure prophylaxis on HIV incidence. So the researcher decides to conduct a randomized trial. Imagine it's a very large trial, perfect follow-up, perfect compliance. And so the researcher randomizes individuals either to pre-exposure prophylaxis or a control. And then he follows the individuals for some time, let's say 1 year, and looks at the number of HIV infections in one group compared to the other group. Okay, at the end of the study, the researcher finds that the treatment reduces the average risk of infection. The researcher is quite satisfied with the design and methods of the study, so they go to a conference and present the results. At the end of the talk, where the researcher has presented the results, another researcher in the audience raises their hand and criticizes the study. So specifically, the second researcher has a problem with the inclusion criteria that were used by the first researcher. And the critique goes as follows. So we know that there are some individuals who are homozygous for the CCR5 delta 32 gene variant, who are resistant to HIV infections. And so they would not have acquired HIV regardless of the treatment arms they were assigned to. So the second researcher argues that we're not interested in the effect in the population that was targeted by the study, but we are interested in the subpopulation of individuals who do not carry the specific gene variant. So the second researcher argues, well, we only want to know the effect among the individuals who do not have this gene variant. So the first researcher thinks about it a little and then takes the criticism too hard, goes back to the lab and decides to conduct a new randomized trial. This randomized trial is exactly identical to the first one. Same population, same design, same treatment, everything is the same. But this time, all the individuals before the start of the trial are screened for this gene variant. And if they are positive for the gene variant, then they are excluded. Okay, so now keeping this setup in mind, a natural question would be, how do the risk difference and the risk ratio change in the second trial compared to the first trial? And imagine that we don't know anything about the prevalence of this gene variant. So here there are some possibilities. Maybe take a second to try to make your guess and figure out what you would answer to the question. And I will tell you right away that the correct answer is that the risk difference will go down, but the risk ratio will remain unchanged. And this may seem a bit puzzling, or at least it was to me the first time I saw this, and I will try to explain why this happens. So to do so, I will introduce the concept of response types or counterfactual types. It's a quite common concept in epidemiology, but just to be a bit more formal, imagine that we have a variable t, which will denote the response type. And we have 4 response types. So the variable t can have values 1, 2, 3, or 4. So individuals who are t equal 1, so first response type, those are individuals that will not develop the outcome under treatment and would not develop the outcome under control. So in other words, those individuals are immune to the outcome. Then we have individuals in t equal 2, which develop the outcome under treatment, but do not develop the outcome under control. So these individuals are the ones that are hurt by the treatment. And then we have individuals in the third response group, t equal 3, which do not develop the outcome under treatment, but develop the outcome under control. So for these individuals, the treatment prevents the outcome. So those are called the prevented. And finally, we have individuals who are doomed. So individuals who would develop the outcome regardless of the treatment you give them. So here I'm using classic counterfactual notation where the superscript indicates which treatment I'm imposing on the individual. Okay, let's assume that there exists a pretreatment variable t that defines the response types. So this is quite a common assumption in epidemiology because you will find it in epidemiology textbooks because it's an easy way to explain what confounding is. The idea is that here we need to imagine that these response types already exist, and then once you get the treatment, we understand which outcome you get based on the response types. But let's assume for a second that these response types exist and they exist before the treatment. We will also assume that there is a positive probability of having the event among individuals under control. So if you enforce everyone to take the control instead of the treatment you're interested in, then you would expect some individuals to have the outcome. This is a benign assumption. It's just done because otherwise the causal risk ratio is not well defined. What is the causal risk ratio? Well, the causal risk ratio is the ratio between the probability of having the outcome in the ward where everyone is treated divided by the probability of having the outcome in the ward in which nobody is treated. So this is the commonly defined causal risk ratio, and under assumption 1, we can rewrite this ratio as a function of the probabilities of being in the different response types. Okay. Let's add another assumption. So imagine we are not interested in the overall population, but we are interested in a subpopulation with a subgroup, which we will indicate with s equal 1. So we introduce now s, which is a binary variable, which has 2 levels, 0 and 1. S equal 1 represent the units that we are interested in, and S equals 0 represents the unit we are not interested in. And now we will require S to fulfill 3 assumptions. So A, the treatment doesn't affect S. B, S is independent of the counterfactual outcome among non-immune individuals. And C, the probability of being in the subpopulation of interest among non-immune individuals is higher than 0. So this seems a bit technical and maybe a bit abstract, but instead of explaining what this actually means, let me give you an example of what S can be to satisfy these assumptions. So imagine that we build a subpopulation S equal 1, which is all the individuals in the general population except the ones that are immune. If you do that, then S will satisfy this assumption. Alternatively, you can imagine S equal 1 as a subpopulation that is built by taking the overall population and sampling immune individuals with a probability and the non-immune individuals with another probability. There are multiple ways to think about S. I think this is a very practical one. So you can imagine S equal 1 to be a population that is built only selecting individuals based on their immune status, if they're immune or not. So under assumptions 1, 2, and 3, the causal risk ratio only among individuals with S equal 1, so in my subpopulation of interest, is equal to the marginal causal risk ratio. So this means that any subpopulation, if you have noticed, I didn't specify exactly how this subpopulation was built. I only said that it was built by selecting based on immune status. So what I'm saying here is that any subpopulation that is defined by selecting individuals only looking at their immune status, so if they're immune or not, will have the same causal risk ratio. So this is a property that we named immune selection stability. I think it's a bit, so what this means again is that if you select based on the immune status only, then the causal risk ratio will be stable. And I believe that there is a simple way to explain this. I think this the proof of this statement is not very complicated, but I think it's even easier when instead of looking at probabilities, we look at absolute numbers. So here I picked this paper from Robbins in 1988. I could have picked any other paper in which they presented this formula. So here Robbins presents the formula for the causal risk difference here, and the formula for the causal risk ratio here, in terms of absolute numbers. So in terms of how many people there are in my sample in the different counterfactual types. Here, the ordering of the counterfactual types is different from the order I gave you before, but that doesn't matter. What matters is that here you can see that the causal risk difference depends on all the counterfactual types, because you have n, which is the total number of individuals in the sample, which will be the sum of individuals in group 1, 2, 3, and 4. And then you have n2 and n3, which are the number of individuals in response type 2 and 3 according to Robbins order. But the causal risk ratio doesn't depend on all the counterfactual types. If you look at the formula, you will notice immediately that there is one counterfactual type missing. And that counterfactual type missing is the immune one. So this is why if you change the number of individuals who are immune, the causal risk ratio doesn't change, because there is nowhere in this formula the absolute number of individuals in the immune group. And I think this is quite intuitive. I want to point out that while this formula it's quite known, and you will find it in a lot of papers like this on some intro epidemiology textbooks, I don't believe that this property has been described. In all of these papers, I couldn't find any mention to this immune selection stability property of the risk ratio compared to the risk difference. So I have argued about this immune selection stability property, and I've done this using counterfactual types or response types. In a way, this is a bit problematic, because you can never know to which counterfactual type a unit belongs to, right? Because in reality, we can only observe one unit under one version of the treatment. So I can know their outcome if they take the treatment or if they don't take the treatment, but I cannot know both. So I have no way to distinguish all the counterfactual types. Indeed, to do so, I would need crossword observation. I would need to be able to observe two different parallel words, which I can't. However, there is an alternative version of immune selection stability that doesn't require joint counterfactuals at all. So let me tell you a bit more about this. Everything we need to know is everything we need to do is just we need to replace the way we define immune individuals. So before I said that immune individuals are individuals that in the word in which they are treated do not develop the outcome, and in the word in which they are not treated, they do not develop the outcome. Now I will define what immune means in a different way. So let's imagine that we have a pre-treatment discrete variable t, which can take values from 1 to k. And now everything I'm saying is that individuals who have t equal 1 have a probability equal to 0 of developing the outcome under treatment, and a probability equal to 0 of developing the outcome under control. So now t equal 1 indicates some units that are immune, in the sense that they have probability of 0 of experiencing the outcome. But I'm not saying that those are all the immune individuals. I'm just saying that those individuals are immune to develop the outcome in this specific sense. This may seem a little technicality, but actually makes a lot of difference, because now this assumption 4 is testable. Specifically, it can be falsified, because if I know what t is, I can recruit individuals that have t equal 1, randomize them either to treatment and control, and then follow them up, and I expect that nobody develops the outcome, right, in this hypothetical trial. If someone develops the outcome in this hypothetical trial, it means that assumption 4 is false. So this is an important distinction compared to assumption 1, which is based on joint counterfactuals. However, the result doesn't actually change. So I can simply replace assumption 1 with assumption 4 and make the same statement. So under assumptions 2, 3, and 4, the causal risk ratio in a subpopulation S equal 1 will be equal to the marginal causal risk ratio, which again means that if I build any subpopulation in a way that this subpopulation is defined by only selecting individuals based on their immune status in this newly defined immune status, all of these populations will have the same causal risk ratio. And we have seen, we've talked a lot about causal risk ratio, but as you can imagine, this immune selection stability property will also hold for deterministic transformations of the causal risk ratio. So for example, the excess causal risk ratio, or in vaccine studies, the vaccine efficacy, which is 1 minus the causal risk ratio. And it will also hold approximately if you have an effect measure that is an approximation of the causal risk ratio, both in the marginal population and in the subpopulation of interest S equal 1. So for example, if the outcome is rare, both in the overall population and the population S equal 1, then the odds ratio will approximate the risk ratio, and so also the odds ratio will be approximately stable to immune selection. And there is also an isomorphic property for the causal survival ratio. The causal survival ratio is I don't know if you're familiar, it's a measure that's sometimes used in epidemiology. It's simply a risk ratio in which you swap the labels of the outcome. So essentially now the causal survival ratio is the ratio between the probability of not having the event under treatment and the probability of not having the event under control. And as you can imagine, as you probably already understood, by the fact that this is simply a risk ratio in which I swap the labels, the causal survival ratio will now be stable to doomed selection. So if I create a population only selecting based on the doomed status instead of the immune status, then the causal survival ratio will stay the same. And let's try to see some hypothetical examples in which this may be useful. So this is the example I presented you at the beginning, our initial motivating example, and I hope by now it's clear why the risk ratio remains the same. So the point is that if you have a randomized trial and you are assessing the effect of pre-exposure prophylaxis on HIV incidence, then the marginal risk ratio that you obtain from this trial will correspond to the effect when you exclude individuals who are homozygous for the gene variant, because these individuals will not experience the outcome under treatment and will not experience the outcome under control. So these individuals are immune. So if I exclude them, the risk ratio doesn't change. But let's look at some other examples. So imagine you want to study the effect of wearing a face mask on COVID-19 infection. And you conduct an RCT and you get a marginal risk ratio. Now, this risk ratio is expected to correspond to the effect when you exclude the individuals who could not have been exposed to the virus, maybe because they were in an area where there was no the virus was not circulating. But so the risk ratio will stay the same, even though you do not necessarily know who these people are. You do not necessarily know who has been exposed to the virus and who has not been exposed to the virus. Or you can imagine an RCT, a randomized trial, where you want to assess the effect of a childbirth subsidy program on having children. So now you can calculate the marginal risk ratio, and this will correspond to the effect when you exclude families who are unable or unwilling to have children. Because if there are some families who will not have children regardless of the treatment they are assigned to, so if they are assigned to the subsidy program or not, then those families are immune in our terminology, and so they will not experience the outcome either way, and so if you exclude them, the risk ratio will stay the same. Or another example, this is from Stanford-Smith, very similar to the face mask example. So if you have a randomized trial to assess the effect of COVID-19 vaccine on COVID-19 incidence, now you calculate the risk ratio from the trial, and this effect, this risk ratio, will correspond to the effect once you exclude individuals who were not exposed to the virus during the study period. And even though you do not necessarily know who these people are, again. And let's see some example of doomed selection stability. So imagine now you have a slightly different study. You want to study the effect of pre-exposure prophylaxis on all-cause mortality. So not on HIV incidence, but on all-cause mortality. So now the marginal survival ratio that you will get from this hypothetical trial will correspond to the effect once you exclude individuals who have a very fatal disease. So if these individuals would die regardless of the treatment they're assigned to, then those individuals are doomed. And therefore, if you exclude them, the survival ratio is not expected to change. Or again, you can take the same randomized trial as before, where we were randomizing COVID-19 vaccine to look at the effect on COVID-19 incidence. Now, the marginal survival ratio, which is simply, you can imagine the outcome now to be not getting COVID, and so calculate the risk ratio, that would be the survival ratio. The marginal survival ratio will correspond to the effect when you exclude individuals who already had COVID at baseline or immediately after baseline. Because these individuals, you can expect, so since you expect that the vaccine will not biologically have an effect immediately, if some individuals was already contracting COVID-19 at baseline, then these individuals are doomed, in the sense they would have gotten COVID regardless of the treatment arm they were assigned to. And therefore, if you exclude them, the marginal survival ratio would not change. Does this mean that we can just ignore, like we can just, does this mean that if we can include immune individuals or not, and this doesn't matter? So I've argued that the causal effect remains the same, right? That the causal risk ratio remains the same if you exclude immune individuals. However, there is a statistical efficiency argument for excluding immune individuals. So for example, so specifically, if you have fewer immune individuals, you will have more precise estimate of the risk ratio. And this becomes clear when you look at the formula for estimating the variability of the risk ratio. So here you have the standard error of the logarithm of the risk ratio estimator, and you can see that this is a function of the number of cases in the treatment arm, the number of cases in the control arm, the total number of units in the treatment arm, and the total number of units in the control arm. And so if you add immune individuals, you will intuitively, you will not change the little n's, so you will not change the number of cases, but you will increase the total number of individuals. So if you add immune individuals, you will increase the standard error and therefore lower the precision of your estimate. So there is an argument for excluding immune individuals, because this will make your statistical inference more precise, even though it will not change the causal estimate of interest. The causal risk ratio will remain the same. So let's just recap what we have said so far. So the relative risk is stable to immune selection. And this is a very simple mathematical fact. Some people may argue even intuitive, but we believe this has not been discussed much. This hasn't been discussed much in the literature. Another important point is that there is an asymmetry between sometimes in the identification. So sometimes it's easier to identify relative effects than absolute effects. So now I'm essentially claiming that I can identify the risk ratio among non-immune individuals, even though I have no idea who these immune individuals are. But I cannot do that for the absolute risk. So I cannot do that for the risk difference, for example. So there is sometimes it's easier to identify relative effects compared to absolute effects. And another point is that this immune selection stability property of the risk ratio may provide a concrete argument for transportability. So it is often said that risk ratios are, so relative effects in general, are more stable across populations. I don't think there is an absolute way to prove this in general. Maybe the immune selection stability can be a way to motivate the stability of the risk ratio in a very specific setting. So for example, if you have a population that you believe can be interpreted as a sample from another population, but only looking at the immune status, or a population that is simply a subset of another population and all the people excluded are immune to the outcome, then you expect the risk ratio to be stable. We have and this is important because this is an argument for transportability of the risk ratio that doesn't rely on assumptions that are untestable. So, for example, I don't know if you're familiar, but there is this great work from Whitfeld and colleagues discussing the transportability of the risk ratio and the survival ratio, and they do so invoking monotonicity, which is an assumption that is a bit hard to justify in certain settings, and in general cannot be tested. And if you're interested in this work, this is our publication. You can find our paper on the American Journal of Epidemiology. And probably now you are thinking either, okay, this is a very trivial mathematical fact, or this is maybe interesting, but I don't see how this can be useful. And in the rest of the talk, I will talk about a specific example in which we believe that thinking about the immune selection stability of the risk ratio would have helped in dealing with this situation. So I will be a bit less mysterious now. To do so, we will go into an applied, in the applied world, and we will talk about screening colonoscopy trials. So this is a joint work with Vanessa Didelets and Matt Stensrud. Vanessa Didelets, who brought this this issue in colonoscopy trial, this debate in screening colonoscopy trials to our attention. So what is screening colonoscopy? So I'm not a medical doctor, so I may say something that is inaccurate, but I hope I will be able to capture the overall idea. So screening colonoscopy is a method to screen for colorectal cancer. It's a particular way of screening. It's a bit different from screening in the classic sense, because the screening procedure has two different aspects to it. So on one hand, during the screening procedure, you can identify individuals who have colorectal cancer or are likely to develop soon colorectal cancer. On the other hand, during the procedure, with the same tool that you use for the assessment, you can actually remove abnormalities in the tissue, so these so-called polyps. And so at the same time, this screening colonoscopy will help you with the diagnosis, but it will also reduce the probability that you will have a diagnosis in the future. So in 2022, there was this publication in the New England Journal of Medicine about the Nordic European Initiative on Colorectal Cancer trial, or Nordic trial for short. This was a very large randomized trial of almost 85,000 individuals between 55 and 64. They were taken from population-based registries in Poland, Norway, and Sweden. The design of the study, it's a bit complex, but for our purposes, the design of the study was you take individuals and you randomize them with a ratio of 1 to 2 to either being invited once for screening colonoscopy or not. And what the researchers found out was that being invited to, so the arm that was invited to screen colonoscopy had a lower risk of colorectal cancer at 10 years compared to the control group, the usual care group. And they estimated a risk ratio of 0.82. This sparked quite some debate because 0.82 was a smaller effect in magnitude compared to previously published results from observational studies. And specifically, there were some criticisms to this trial, but here we will focus on one, which is this critique of a prevalence bias. So there were some authors who criticized the Nordic trial because of what they named a prevalence bias. I will explain this in a minute. We will focus here on this article specifically because I think from Brenner and colleagues, because I think they do a good job in summarizing what is their thought process to criticize the design of the Nordic trial. So in this essay, the authors essentially claim the following. So if you already have colorectal cancer in the moment you do a screening colonoscopy, then there is no chance that the screening colonoscopy will reduce your risk of developing cancer, right? It will just assess that you have colorectal cancer or not, but it will not reduce the risk in the future. So the presence of these prevalent cases at baseline is interpreted from these researchers as a problem. So indeed, they claim that the exclusion of prevalent cases is an important prerequisite of a proper randomized trial that has this type of question. And what they did was then they took the data from the aggregated data from the Nordic trial, and what they did was they imagined, so they made some guesses about what could have been the prevalence of prevalent cases, so the proportion of prevalent cases at baseline in the study, and then they redid the analysis by excluding these individuals. So, and they show that when you do that, the risk ratio changes substantially. And this led these authors to conclude that the presence of these prevalent cases at baseline, so the presence of these cases of colorectal cancer that could not have been prevented by the screening, leads to the fact that the risk ratio that they report in the Nordic trial is actually an underestimation of the true effect. So this is not really a question of bias, in my opinion, and in the sense that it's more like the authors of this essay, so Brenner and colleagues, they have in mind clearly a different causal estimate. And this becomes very clear when they try to explain what would be the ideal trial that they would run. So we hear a lot about how target trials can help us reason about research question, and I think this is a good example. So here, Brenner and colleagues describe this hypothetical trial in which you take your population of interest, you look at who has colorectal cancer and who doesn't, and then you exclude the individuals who have colorectal cancer, and only the one who don't have colorectal cancer, you randomize them to either screening colonoscopy or not. And obviously, as the authors say, this approach is both unethical and unfeasible. But this gives an idea of what is the problem they have with the study. So essentially, the controversy is around what is the intended target population of the trial. So what is the intended target population we are interested in? So is it the population that is generally eligible to attend screening colonoscopy, or is the population that is free of colorectal cancer? And this debate is, it's unclear which one, so there are different opinions on which target population we should aim for. For example, in this commentary from Song and Brett Tower, who is one of the original author of the Nordic trial, they argue that yes, they acknowledge that the presence of prevalent cases is a problem, but they do not believe that there are reliable statistical analyses to tease out these two components of the screening procedure, and so they believe that it's safer to stick with the results to stick with the analysis as the one reported in the Nordic trial. On the other hand, there is this article recently published in the American Journal of Epidemiology from Breitmeyer and colleagues, in which they argue that the quantity of interest from a public health perspective is the effect among the people who are eligible and not among the people who do not have the colorectal cancer, because you do not know essentially who has colorectal cancer before doing the screening. Our contribution to this debate will be a bit different. But just to recap, what is the reasoning of this prevalent bias? What is the rationale of Brenner and colleagues to argue that there is a prevalence bias? So first, they claim some trial participants already have colorectal cancer baseline, so the screening procedure cannot prevent the outcome in these prevalent cases, and therefore the effect we're interested in is the effect among the non-prevalent cases, and therefore they believe that the Nordic trial is an underestimation of the true effect they care about. But if you look at this 4 lines, you will notice that this is it's very, very similar to our HIV motivating example. In fact, we believe that this immune selection stability and the immune selection stability of the risk ratio in this case will help us say something about this controversy, because we can show that the question of the population does not matter if we choose certain contrasts. What do I mean by that? So let me give you a numerical example. So here, this is the table from the paper from Brenner and colleagues in the European Journal of Epidemiology 2023. I will explain it in a minute, but for now, the only thing I will say is that we focus on this part, the intention to screen analysis, and we drop this second line because I believe there is a typo in it, so just to avoid distraction. So this is what the authors did. So in the first line, you can see the data, the results reported from the Nordic trial. So here you have the risk in the treatment arm, and so 0.98%. And here you have the risk of colorectal cancer at 10 years in the control arm, 1.20%. So the risk ratio reported from the trial, which is 0.82, which corresponds to a risk reduction of 18%. Risk reduction is simply 1 minus the risk ratio, expressed in percentage. And what the authors do is that they say, okay, let's imagine, this is a theoretical minimum, let's imagine that the proportion of prevalent cases at baseline is 0.22%. And now they redo the calculations for the 2 risks by taking these people out both from the numerator and the denominator, so as if the prevalent cases were excluded, and they calculate a different risk under treatment and a different risk under control. And they obtain a different risk ratio. And then they do this for different possible prevalences of prevalent colorectal cancers at baseline. And what you can see is that the risk ratio goes from 0.82 to 0.48. So quite a change. However, what you can notice from this table is that if you calculate the survival ratio, it will be identical in all the scenarios. And if you calculate the risk difference, it will be identical in all these scenarios. So the survival ratio is just 1.0022 for all these 5 scenarios, and the risk difference is just minus 0.22 for all these 5 scenarios. So it's true what Brenner and colleagues say, that the risk ratio varies dramatically in this setting, across these different hypothetical scenarios, but the survival ratio and the risk difference do not change, which means that the risk difference that was reported in the Nordic trial corresponds to the risk difference when excluding prevalent cases in all of the scenarios proposed by Brenner and colleagues. And in a way, we were doomed to succeed because the authors assumed two things. One, they assume that you have the same proportion of prevalent cases, both in the treatment arm and in control arm. And this makes sense because individuals were randomized, so you would expect a similar prevalence. And they are also implicitly assuming that the prevalent case would always be diagnosed with colorectal cancer during the 10-year study period. So regardless of which treatment arm you end up in, if you already have colorectal cancer, I expect you to get a diagnosis in the next 10 years. So they have defined prevalent cases at baseline as doomed individuals because they are doomed to receive the diagnosis of colorectal cancer regardless of the treatment. And this is a formalization of, for example, this statement that Brenner and colleagues did in another paper where they say there is no way screening could have prevented these prevalent cancers, even though it could have led to their earlier detection. So they imagine that a prevalent cancer would be diagnosed anyway at some point, and if you do, the only difference is that if you are in the screening arm, you will be diagnosed immediately. If you are not in the screening arm, you will be diagnosed at some point during these 10 years. But we know that the survival ratio is stable to doom selection, and we also know that when the outcome is rare under no treatment, the risk difference is a simple transformation of the survival ratio. So to be a bit more formal about it, we can define the causal risk difference as the difference between the probability of the outcome under treatment and the probability of the outcome under control, and the causal survival ratio, which is simply 1 minus the probability of the outcome under treatment divided 1 minus the probability of the outcome under control, which is the same as the definition I did above, I gave above. And then you can define the same causal effects, but conditional on p equals 0, where p is just a binary variable that tells me if you are a prevalent case at baseline or not. So if p equals 1, you are a prevalent case at baseline. P equals 0, you are not a prevalent case at baseline. And now, under this simple set of assumptions, so obviously it's an interesting case where there are no prevalent cases at all, because then obviously it makes no difference if you exclude them or not. But let's say there are some prevalent cases, but not all the individuals in the trial are prevalent cases. And let's say that the risk of the outcome under no treatment is low, which is the case in this trial where I believe the risk under no treatment was something like 1.5%, if I remember correctly. So pretty low. And then if you assume that the prevalent cases have a probability of 1 of being diagnosed either under treatment or under control, then under these three assumptions, we can show that the causal survival ratio marginally is the same as the causal survival ratio among non-prevalent cases. And the causal risk difference from the entire population will approximate the causal risk difference among non-prevalent cases. Here, there should be a note of caution in the sense that this assumption that all the prevalent cases are doomed may be violated if the length of the study is short, or if there are competing events, so for example, death, or if screening leads to overdiagnosis. Because essentially, this assumption relies on the fact that if you end up in the control arm, you will be diagnosed anyway. So if you die before receiving a diagnosis, then you will not be diagnosed anyway. Or if the study is very short, you will not get a diagnosis by the end of the study. But let's say you have a sufficiently long follow-up, and the Nordic trial has a follow-up of 10 years, which seems reasonable. You have a population of young adults, so death is rare, and you do not believe that overdiagnoses are likely, then the doomed assumption is plausible. So we are saying, in other words, that in this context of screening colonoscopy, if a researcher is interested in the risk difference rather than the risk ratio, then the effect in the whole population is an adequate approximation of the effect only among units that do not have the disease at baseline. So there is no need to count who are the prevalent cases, which is like we do not actually know who is a prevalent case at baseline and who is not. But we do not need to know who is a prevalent case and who is not if we are interested in the risk difference only among non-prevalent cases, because then we know that that's the same as the risk difference in the overall population. And these results apply potentially also to other screening methods. So for example, a similar critique of relevance bias has been advanced towards flexible sigmoidoscopy randomized trials, so another type of colorectal cancer screening. If you're interested in this debate and our contribution to it, our article will appear very soon, I think in a matter of days, in the European Journal of Epidemiology. And with this, I can conclude and happy to take any questions.